So I think we stop at covariant derivative and introducing the Christoffel symbols. We'll continue to talk about how you evaluate the Christoffel symbol and look at its property. But, the covariant derivative is defined by this relation 4.57. So basically now we start from taking a derivative of the vector, a vector v, will q full superscript j. And that is defined with this symbol. So v semicolon, yeah, j, instead of a comma j, use a semicolon j, and then contraction with k component of this with the k component of the base covariant basis method. Okay, so that is the how you define this covariant derivative in terms of the whole vector. So this covariant derivative is in itself is defined by this the k component, also vk of the qj, and then add another term, this v mu down k and j mu or mu j. We see that this order is unimportant later. Okay, that is the Christoffel symbol, and this is what we call the second kind, and pretty soon we'll see the first kind, and that is defined by the, first we define this by saying that this is a coefficient. This is the coefficient of taking the derivative of the basis vector epsilon k with respect to another coordinate j, and project on all the basis vectors. So the gamma mu jk epsilon. So this is the mu component of this derivative of the basis vector. Okay, that's how you define this Christoffel symbol. Okay, and now this is not an explicit equation for to express that, and I mean it's not this quantity equals to something. So we want to basically solve this for the coefficient, and to do that is quite trivial, right? Because this is just a component. So in user vector, we just dot into another basis, and that would give you a particle delta, and then you can do that. But for these covariant basis, it's not orthogonal to another covariant basis. It's orthogonal to a contravariant basis. So if you remember that we talked about that before, right? So it's that is this. It's orthogonal in this sense. In this case, we want to dot into a contravariant basis. So, for example, we already have j and k. We have sum over mu. We can like dot into a contravariant basis epsilon I. So that if you this dot into that, and using that, this would be a conical delta I mu, right? This dot into this one, using this one, right? So now you can sum over mu, and that gives you just one coefficient. Okay, so That is this equation, except I'm not using exactly the same indices label for the text. This is 4.54. The text we use n is still I. So it doesn't matter. Right? So this quantity is defined. Now you can solve this coefficient. The Christoffel symbol is equals to this one. Is that okay? Look, now we are making progress to calculate this. So as long as you know this, all these epsilon, or the basis, covariant basis, contravariant basis, you can just do this derivative and dot product, and then you can calculate that, and which is fine if you have a transformation that allows you to calculate all the coefficient. I mean that all the basis vector, but that is possible when you do a nonlinear transformation. We start with a Cartesian coordinate and do a nonlinear transformation. We define all these basis vector. These exist in that sense, but if you want to extend it to a even more general situation where you don't necessarily define this epsilon, or it can be defined, but then it may be not that useful to define them, and you want to do some intrinsic property, and which is defined by the metric tensor. And basically later on we'll try to solve for this using the metric tensor and the derivative, basically the derivative metric tensor component. We'll do that later, which is pretty soon, hopefully. Yeah, and but after you yeah, yeah, no problem, no problem.
You talked about that symbol.
Yeah.
Become that way, so it's like orthogonal vectors, or not necessarily orthogonal vectors.
Not necessarily what?
You talked about, well, you find that that epsilon I, the top one is giving us valid for the orthogonal component.
This one?
Yes.
Yeah.
So
this is how you the relationship between the contravariant basis and the covariant basis. That we define that.
Okay. So for this case, just general case, for our.
Now this is using this to solve for this. So last time we defined this, all this gamma by this relation. We require that this is just basically the component of this derivative in the mu direction, or the mu basis vector, covariant basis. These are just basically defined as coefficient. This is to solve it explicitly. So this is this contract with this equals to that. So you need to reverse the order and solve this in terms of this one. So basically, this one equals this one. Okay, and to do that, they basically dot into something that is orthogonal to these bases, but they are not the covariant bases. Covariant bases is generally not the orthogonal to each other, but you need to use a contravariant basis and use this relationship to do that. Is okay? All right, now with this relation, you can do first look at the property of this the gamma, the Christoffel symbol. The first thing you can show is that the order of these two indices in the subscript j and k, the order is not important, right? And we'll do that by the definition of epsilon, because you remember this epsilon, like write this epsilon k. This epsilon k basically is using the Cartesian coordinate. This is partial x, let's just use and using the unit vector in the Cartesian coordinate. Unit vector. Right. This is transformed like a covariant component. This right, and now you can use this one and substitute into this one, right? With this one, you can say this equals to that and also equals to and just dot in the substitute this in here, except that I cannot use I. Like I cannot use J or also IJK. We cannot use K. I mean, this is already K. Let's say L. Okay. Partial Q. Partial QJ is this one. We keep the partial QJ and this partial QJ here, right? And then you have EL, something like that, right? It's substitute this with that and take this derivative equals to that and dot into that, this one, right? And now you can see explicitly you can interchange J and K because this partial derivative, the order is reversible. The partial derivative, the order doesn't change the partial derivative. Right? You can see if you write it in Excel, right? It's just essentially the same. And then you can now identify this is epsilon. This is epsilon I dot in the partial epsilon J partial QK. Right? This is by this definition, this is just page with these two are the same. Okay, so the Christoffel symbol, the two subscript interchangeable, the order, which is very convenient later on in what we're trying to do to solve for this in terms of the metric tensor is quite useful. Okay, you got this. So this is how you show that the subscripts are interchangeable. All right, and now with more people, anyone have question or homework can ask me when we have some time. If you have a homework question, but let's continue a little bit. You can interrupt me if you wanted me to talk about a homework problem. But before we do that, we can use this one by one more time. Right now, this is what we mentioned last time. This Christoffel symbols. They are not. It looks like a third rank tensor, but they are not tensor. And likewise, we already show that just this term is not the tensor. Just these partial derivatives. So you need to combine the second term with the Christoffel symbol with this, then the whole thing is a tensor. And you know, it's not difficult to show. It's just you need to just follow the rule. And you can use that once we have this explicit expression. We can try to write down the transformation rule for this gamma. Let's just copy that and work on that a little bit, and to see explicitly why this is it in itself is not a tensor. Just copy this equation because now it's not writing in a very good form. So copy this here, gamma n jk is epsilon I superscript epsilon k or the other way around. We already saw that they are interchangeable, right? Then we could work out the transformation rule by just following the steps. Right now, there's a homework. The homework for this tensor, I think I do after next week, Monday after next week. You saw that because next week I won't be here, so it's the Monday after next week. Then we can just work out, say, in the pine coordinate, right? Okay. right? But with the pi, you just change everything to pi, right? With pi, you just this pi and this pi, everything becomes pi, and you see that and everything you transform by either the contravariant transformation rule or the covariant transformation rule. So for this contravariant vector, so this would be partial. This is partial qi pi because we transform to pi, right? And partial q. Now you use another index ijkl, right? And then epsilon l. Right? That's how you transform a contravariant index, right? That's this one, and then this is start into. Now you transform the derivative also. The derivative is covariant, so it's the other way around. So it's partial q pi j, and then we need another index LLM, right? This is partial q. I may actually start with this. So this one, we want to transform this one to this one. So I just not writing. So at first we start with this one, right? Start with this in the prime coordinate. Everything in the prime coordinate. So this transform to this one. This derivative transform to this one, right? And then the epsilon k, which is another covariant quantity. So again, it's partial q pi. This is k, and so another index n, right? And then now this is epsilon n. Right? You just follow the rule and then do that. Now you can simplify now. The first, this one just copy. I. And now this one you can take out. This one is nothing. This is just a number. And now for this one, there are two terms, right? One is the derivative of this. I forgot this. This is n. Right? Sum over n. Yeah. One is operate on the transformation matrix. The other is on the vector. If you working derivative of the vector, then this becomes a number again. So partial qn, pi k, and then epsilon l dot into. So there are two terms. The first term is from l dot into partial. I should say the bracket. The first term is operate on this one with this as a number. Dot into wait, this is q pi. This is transforming this one. Yeah. So this, I think this is fine. But this is partial qn. Wait. And then the second one is operate on this one. Outside. Um concrete. Right. So this is how you transform, and you identify this is your Christoffel symbol in using the same rule. This is L, right? This is L, and then N and N or M and N doesn't matter. You already saw that. So we saw that if you just keep the first term, we assume the second term is 0. Basically, it's saying that the second derivative is 0 or this transformation is linear, then you don't have this second term. Then now you can confirm that this 3 matrix combined is the transformation rule of a mixed tensor with a 1 contrarian index and 2 covariant indices, right? That's the contrarian index. You transform like this one, right? Did I get all the emails correct? Yeah. And then n and m, yeah, right. Right. The first term is how you transform a third rank tensor, third rank mixed tensor. But it's not transformed like that. You have the second term. Generally, you have the second term. So therefore, this gamma is not a third rank tensor because of the second one, second term. Okay. So that is. I mean, although this is quite long, so the whole thing is quite complicated, but um, at least you see that the second one, second term will. It's the reason why this is not tensor. It's basically you need to take the derivative of the transformation matrix. The transformation is nonlinear, so the second term is non-zero. Therefore, the whole thing is not a tensor, right? But you can also use that. Once you have that, you can also use that to transform this covariant derivative, and that is basically the same. So if you like, you can work that out with the algebra may be a little large, so work out the transformation of the first term and the second term. Now that you have how you transform this one, so like write everything in pi, just like what I did here, and follow the transformation rule of the derivative, and then the vector, and then this one, and then convince yourself that this one, the whole thing transform like a tensor now. And the reason is that after you do that, you see that this transformation will involve a second derivative of the transformation matrix. But the first term also involves a second transformation because you have this V transform, like a V to V prime, you have a transformation matrix in the V, and they take the derivative with respect to coordinate also. So the first term also have a second derivative, and this second derivative will cancel the second derivative of the second term, right? And you can see that how you show that. Although you write down the whole thing will be a little bit long, so I'll just tell you the procedure how you do it, right? So you can see, and the reason is that by adding this second term, the two terms involving second derivative will cancel each other. So the whole thing will now transform as a tensor. This one is transformed like a second rank tensor, second rank mixed tensor, this covariant derivative. Okay, so that's why we define this covariant derivative, because that is how you're expecting to express your equation, right? And there's another way to find something called that is transformed like a tensor even with this one. And later on, I think there's a homework problem to show that if you subtract the two, right, then found is anti-symmetric tensor. Like if you just have this one, you subtract something, just reverse your indices. Then that one also is a tensor. This is although this is taking just the ordinary derivative, not covariant derivative. But after you subtract that with interchanging the indices, then they becomes a tensor again. And the reason is just the same. You work out a transformation, you see that they cancel the second derivative of the because both terms now involve derivative over the transformation, and then the two will cancel each other, and then the whole thing will transform as a tensor. So that would be a homework problem. Okay, so so all these the property that we can get once we solve for this one. So once we have this relation, we solve the Christoffel symbol. But now we try to move on to find an equation to solve for this object using just the metric tensor. Okay, and now to do that, we first define something. Okay, we need to find some space. We already done all this discussion. Okay, so now we move on. So first, we want to define something with all these indices in the subscript. So basically, we want to move this down, move this superscript down, and to do that, we just multiply by a covariant metric tensor. So like G, we already use IJK. Let's use L, IJK L, and contract with I. Right, we do that. Right. Although this is not a tensor, but we can still do this operation. This is just a matrix multiplication to contract a subscript with a superscript this way. And you can see that how you do that by using this definition. So we have G L I epsilon I dot E epsilon K. Right. Let's use this equals to that and substitute in here. We get this one. Right. And now this contraction we already work that out. So a contraction with the countervariant basis with a covariant metric tensor, we just lower the index, will give you the covariant basis. Okay. 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 Good. And now we define this as the Christoffel symbol of the first kind. And in your textbook, let's compare the textbook because the order is at first is defined by this how you put the position. So I is the component that your textbook using this bracket, and it has two slots. The first slot has two indices. The second slot has one index. So this one is the vector I. So that is in equation 4.60. Although again, I'm not using the same symbol. So according to your textbook definition, this one go into the second slot, and then the vector go into the first one. K going into okay. However, obviously that we already discussed that using the definition of covariant basis, right? And then you see that you can exchange two indices doesn't change the value because that's how you define this epsilon. And so you can say that this is okay. It doesn't matter. You can interchange the position, and that we'll use that property again. Very useful. It's okay. So this is how you define the first kind. The labels are, I mean, this is Garmin, and this is using the square bracket. And not too symmetric. So many authors, I think many books are using the same gamma, right? So and put all these in the subscript. Say this is gamma. And now the position becomes a little bit not so uniform. Right. Some people put this I in front. So I take take right. Put the just so the symmetric indices are the second and the third one. So using this convention, the first one is the separate one, which is in this case. So there's some ambiguity in writing it that way. So some people will put the first this one in the middle. So we put in the middle also. So it depends on how you define that. And to remove the ambiguity, you probably will use something like this, a gamma with a bracket, and separate the two. Or you can say this is J. And just to use this notation to separate the three indices into two groups. The first group you can interchange the two; it's symmetric in the first group. But if you write like that, then you see that the gamma is redundant. You don't need the gamma because all you need is the how you describe the subscripts. So you might as well just write it like that. Okay, so that's the way why these two Christoffel symbols, they are not exactly using the same form. This is with a gamma. This one doesn't have a gamma, right? But that's nothing. That's just you just need to get used to that. It's okay. And so this first kind involve a dot product with covariant basis. So derivative is the derivative of covariant basis and then dot into covariant basis. The second kind is the derivative dot into a contrariant basis. All right, so that's the difference, right? And once you have that, obviously you can inverse that and solve for this second kind in terms of this first kind. So once you have that, you can now do another contraction with a contrariant basis. G, like you already have L, like L and L, and then G, L, I, K, right? But this is the delta, conic delta, this talk about that. The contrariant metric tensor is the inverse of the covariant metric tensor. So this contraction gives you a conic delta. Is delta n I. And then sum over I give you and the right hand side is just the contraction with this contrariant metric tensor with this one. So you have L. Here's the L.
Shouldn't be epsilon L instead of epsilon I in second.
Yeah. This is Li, so this gives an L. Yeah. It's the L. Right. Yeah. Okay. So this is GL. So right. So basically, now you too many. Yeah. This equation. This is the equation. So if you have the first kind, then you can contract with a contrariant metric tensor, and then get the second. And this line is kept when you have after you have the second kind, you contract with a covariant metric tensor, you get the first kind. So that is just like the usual way of change rising or lowering the indices. Okay. Now come to what we try to do. So you have this derivative, and then this dot product is both covariant basis vector, and then we can use the property that the G covariant metric tensor is basically is defined by the dot product of covariant bases. That's the definition. And then we can now work out the derivative. Let's use the textbook's way of writing it. Gamma G on partial cube. Okay. Now work this out. But this is this partial cube. Okay, and epsilon I dot epsilon J. Right? And then so with that will involve two terms. The one is epsilon I dot into partial epsilon J as a Q K. The other is epsilon J dot into partial epsilon I. Right? And then now following the rule, following the definition, they're using basically this line. So whatever the vector, the basis vector you dot into will go in the second slot. So for the first term, the second slot is I, and then the first slot will involve J and K. The order doesn't actually matter, but just because of this relationship. But following this definition, you use this one going into the first one, so it's J K. Right, just according to this definition. And then the second one here, with the second slot is, and then the first slot is okay. So now we're getting close. So if you take the derivative of the metric tensor, one component, you get two Christoffel symbols of the first kind. Now the idea is how do you inverse that and solve one of these in terms of a combination of the derivative of the metric tensor components. And now that involves some trick. I think using your textbooks, you want to solve IJK. Actually solve let's erase something. Some space. So you want to solve according to what the textbook want to do. IJ. You want to solve that in terms of the derivative of this one. Now the trick is that using this symmetric notation, right? You see that whenever you take the component Gij with the Ij the subscripts, so you get two Christoffel symbol, one with the I in the second slot, the other one with the J in the second slot. Okay, so that's one property. And then once you fix the second slot, the first slot doesn't matter, the order doesn't matter, you can interchange the two, right? So you want to have a K component, you can introduce two more of these, one with G involving I and K, the other involving J and K, right? And each one will have one term with the second slot has an I, and the other term has a second slot with a J, right? And then you can subtract this from the extra two terms and cancel these two terms. And what is left is just the term with a K in the second slot, which is what you want, right? This is a little too fast or too abstract. That we want to say, we don't know if we can do that, but if we want to do something similar, first we want to subtract this from two other terms. One term has I and K and G, and the derivative obviously is the other one, IG, this will be J, right? And then the other term has J and K in the metric tensor, and then the other derivative obviously is Q, right? And then subtract this one. Right. According to this rule, then you have two terms. This two, after the subtraction, you cancel two terms of this. Cancel one term in here, cancel one term in here because of this rule. And then the other term, what is left is this one has a K in the second slot, this one has a K in the second slot. But the first slot has two indices that the order is arbitrary, so you combine to this. So you need to divide it by 2. Right? So this is, can you see that? We can actually write it down, write it out explicitly. So let's just write it out. C spaces, so 1/2. Let's just use curly because we'll involve all the square brackets, so use curly bracket. So according to this rule, the first one has two terms. One is I in the second slot, the other is J in the second slot. And by comparing this one, K is in the derivative always in the second. The derivative always in the second. So the J into R into the rest is K. Right. It doesn't matter who. This one has again. This one has a J in second. Wait. No, this one. I take that back. Yeah, the second one has a K in the second slot. Yeah. And then the second one has a K in the second one, I and J, and the K, the derivative are in the second one. Yeah. Now this one has a J in the second slot, and also has a K in the second slot, and I is in the second position, and the rest is a K. This is J. Right. These are these two terms, and then subtract the original one. Now you can do cancellation. This JKI, this JKJI, this is JKI, but they are the same because of this rule. So you cancel this one. And this J, IKJ, this KIJ, cancel also. And this two, IJK and JIK, they are actually the same. And they divided by half, which is this one. It's okay. So now this is the formula. This becomes the formula for solving the Christoffel symbol of the first kind. Right? You can just take derivative of the different components of the metric tensor and calculate this Christoffel symbol, this one. And once you have that, you can use this formula to calculate the Christoffel symbol of the second kind by now you just contract with another metric tensor, a contrary metric tensor, and you get the second kind. Okay, so the formula is straightforward. That would be 4.63. It's okay. So now this is how we try to do, and then finally we get the formula. It's slightly complicated, but it's straightforward. Right? So that is I think up to 4.63. Okay, up to you. Any question?